In this final video, I will work through question 3 from the readings from Wednesday. So in the last two videos, I worked through questions from the reading on Monday, and now we've moved on to Wednesday. And what is important about Wednesday is that we introduced Bayes' theorem. And this question here is exactly asking us to apply Bayes' theorem to solve the question. Now, what is the question? Well, we're supposing that someone, and we'll call this someone George, has flu-like symptoms at the height of flu season. Okay, so this person notices they have some symptoms of the flu. And now we ask, what is the probability that this person has the flu given that they have symptoms? So what is a conditional probability of this person having the flu given they have some symptoms? And in this setup here, we're told a bunch of information about other probabilities that when we apply Bayes' theorem to the probability of the person having the flu given symptoms, all of this information here will fill out the right-hand side and allow us to calculate this probability. Okay, so what we're told is that the overall probability of anyone having the flu at this time is 1 over 100. Okay, so I guess it's a small typo here, but please disregard it. What this second sentence here is telling us nonetheless is that at the height of flu season, roughly 1 in 100 people have the flu. So what we can think is that this is saying that the probability of George having the flu is 1 over 100. So we'll use the letter F to stand for George has the flu, or this person has the flu. So the probability of F is 1 over 100, or 1%. Now it does not give us the answer to the question, because the question is asking us, what's the probability that he has the flu given he has some symptoms? Okay, now this here is just telling us the base rate, or the unconditional probability, regardless of whether he has symptoms or not, that he might have the flu, which is 1 in 100. Okay, but we need more information than just the probability that he has the flu as a base rate. We need to know some more, so the rest of the question setup tells us this. So the second sentence tells us that among people who have the flu or the virus, only half of them show symptoms. So what that tells us is that the probability of symptoms given the flu equals 1/2. Now we need another piece of information. What we have here is the probability that someone who doesn't have the flu will have those symptoms. So this final couple sentences, or the final sentence to be specific, tells us that 1 in 20 people who don't have the flu still nonetheless show these symptoms. Okay, so what that is to say is that the probability of symptoms, or S, given not F, or not having the flu, equals 1 over 20. Okay, so now I'm going to flip over to writing out the answer. All right, so let me first write out the information that we took from the setup. So first of all, though, we're wondering, what is the probability of F, this person George, having the flu, given that he has some certain symptoms? Okay, this is what the question is asking us. And now here is what we know from this setup. We know the probability of the flu as a base rate in the population is 1 over 100. At this time of year, just overall 1 over 100 people have it. We also know that the probability of someone showing symptoms, if they have the flu, is 1/2. And now we also know that the probability of someone showing symptoms, if they don't have the flu, is 1 over 20. Now there's one more thing we have to do, is that we also have to know the probability of not having the flu. And that can be simply obtained by subtracting the probability of F from 1. And this is according to our rule for calculating negations, which was just talked about on Monday. All right, so we have all of this information here. Now, what I'm going to do is I'm going to apply Bayes' theorem to the probability of F given S, and we'll see how all this information can help us. Okay, but I'm going to do this in a couple steps, just so that I can try to make it clear how to reason like this to solve other questions. So the general theorem, so not just applied to F or S, but in general for phi and psi, no matter what those sentences are, what Bayes' theorem tells us is that the probability of phi given psi equals the probability of psi given phi times the probability of phi. And the short version discussed in the lecture and the reading simply puts the probability of psi on the bottom. Okay. So, but now when we want to apply this to this question, there's a couple things to note. The first thing is that phi is being instantiated by F, because we're interested in the probability of F given S. So in this case, we have to think of phi as F and psi as S. Okay. So what this means is that in the numerator, we'll have the probability of S given F times the probability of F, and we have those two things. So we have this, and we have this. So we have the numerator. But if you look, we're actually not told directly by the question what the denominator is, the probability of S. So there's something more we have to do. And if you recall from Monday, and actually just the video, the question I worked through in the previous video just now, you'll recall there's something called the law of total probability. And applied to psi, what it tells us is that probability of psi equals probability of psi given phi times the probability of phi plus the probability of psi given not phi times the probability of not phi. Excuse the terrible writing there. Okay, so this is a law of total probability. And so given this law, we can substitute this complicated thing into the denominator. And that gives us the long or the full Bayes' theorem. So essentially what we do is we compute this law of total probability, and then we combine that with the numerator, which we know. And the reason why we can figure out the law of total probability is because, look, the first term that we're summing up is actually just the numerator repeated. So we already have those probabilities from the question. And then the second term, though, we're asking the probability of psi given not phi and the probability of not phi. And in that case, that's exactly the other two probabilities which were given, the probability of S given not F and the probability of not F. So the question gives us all of this information to calculate the probability of psi, i.e. the denominator of the short version of Bayes' theorem. Now I want to make one quick comment, which is that these first two questions, right? What question 2 asks us about this fancy setup with pulling marbles from possibly two different types of urns and wondering what the probability you're drawing from one type, given that you've drawn a yellow. So to answer this question, you have to apply Bayes' theorem. So we're asking, what's the probability that the urn you're drawing from is type B, given that it's a yellow marble? And if you apply Bayes' theorem, the short version of it, you'll find that the denominator will be the probability of a yellow. And this doesn't tell us directly the probability of a yellow, but if you apply the law of total probability to the probability of yellow, you'll see that you do have enough information to answer. So basically you can just figure out the probability of a yellow marble by using the law of total probability, and then plug that into the denominator of the short version of Bayes' theorem, to get the answer, okay? But in this question, and basically all the other questions to follow, we won't break it down into 2 steps. Rather, what's probably easiest is just simply to apply Bayes' full theorem, which is simply where you don't write probability of psi here. You write out the entire law of total probability and then just plug in all of these values that you're given. So I'm going to clear this out, and then I'll write out the full Bayes' theorem and then plug in the values. And also I'll write it out as applied to F and S. So here we go. Now we can finally just simply solve this question. So applying Bayes' theorem, the probability of George having the flu, the probability of F, given that he has symptoms, equals the probability that he has symptoms, given that he has a flu, times the probability that he has a flu, over, and then here we simply repeat the numerator. So over that same sum, or product, sorry. Then you add the probability of the symptoms given not having the flu. And you multiply that by the probability of not having the flu. So another way of thinking about this is kind of the weighted average of having symptoms, in a sense. In any case, now if you recall the numbers given by the question says that the question says that half the people who actually have the flu actually show symptoms. So this first number is 1/2. And then the question also says that the base rate in the population of having the flu is just 1%. So the probability of having the flu, the unconditional probability of George having the flu is 1/100. Now we have to fill out this. So again, we just repeat the numerator. And then we have to add now the other values. So the probability that someone is showing these symptoms without having the flu, so other kind of possible causes for symptoms, like for instance allergies or whatever, means that it's a 1/20 chance of someone showing the symptoms if they don't have the flu. So that in the question gives us that. And then since the question tells us that the probability of F is 1/100, we know that the probability of not F is 99/100. Okay, and now the rest is simple math. So what I'll do first is, you could just simply plug this into a calculator of any type, but I'll just quickly work through this by hand. So the first thing we want to do is just pull out all of these 1/100s. So what we get then is 1/2 over 1/2 plus 99/20. And then what we'll do is increase these fractions up to so that the denominator is 20. So we'll have 10/20 over 10/20 plus 99/20. And that will mean that we have 10/20 over 109/20. And then these will cancel out. So what we'll get is 10/109 as our answer for the probability that he has a flu, given that he has symptoms. And the interesting thing to connect this to what was discussed in the lecture about the base rate fallacy is that even though it's pretty likely, even though half the people, 50% of the people who have the flu show symptoms, it's actually not very likely that George has the flu if he shows the symptoms. And a big part of that is that it's actually so unlikely as a base rate that he has the flu. And there's many other, there's a huge chance that he doesn't have the flu as a base rate. And there's also possibilities that if he doesn't have the flu, he'll still show those symptoms. So when we take into account the base rate and the probability of him showing those symptoms without having the flu, we see that just because half the people who have the flu show symptoms, the probability that he has the flu, given that he does show those symptoms, is actually much less than 50%. It's, in this case, is only 10 over 109. Okay, so now let's quickly just shift back to this, and we see that the right answer is 10 over 109. Okay, so good luck everyone with the rest of the questions and the questions on the problem set.